A very good day to Dr. Idawati. Today, our group would like to present our project with title BGP Case Study. So first, my name is Gateway Yuan. My metric number is 230-828. And next, to my teammates.
Uh, my name is Muhammad Naim Ramil Ramdan. My matrix number is 227594.
Okay, thank you, Imran. Okay, next is me. My name is Muhammad Emarusdi bin Zakaria. My matric number is 229295.
Next is me. My name is Muhammad Zulfikar bin Zul Asar Al Jun, and my metric number is 228828.
My name is Li Rong, and my metric number is 226816.
All right, thank you guys. So let's move to our first topic about what is actually the BGP.
So basically, BGP is a border gateway protocol is the postal service of the internet. When someone drop a letter into a mailbox, the postal service process that piece of mail and choose a fast, efficient route to deliver that letter to its recipients. Similarly, when someone submit data via the internet, BGP is responsible for looking at all of the available paths that data could travel and picking the best routes, which usually means hopping between autonomous systems. For the example, BGP is the protocol that makes the internet works by enable data routing. When a user in Singapore load a website with origin server in Argentina, BGP is the protocol that enables that communication to happen quickly and efficiently.
Right, thank you, Ayman. So next, we move on to when we need to use the BGP. So first is about the connecting multiple autonomous system. So when the routing traffic between different administrative domains, such as an enterprise network connecting to an internet service provider, which is ISP, and peering with one another. So this system is a network that under a single administrative enterprise. So when we need to share a routing information with the outside world, we use the external BGP. It will allow different administrative domains to talk each other without exposing their internal and private network topologies. So the second one is multi-homing. So when we are managing a network that cannot afford any downtime, and we purchase the links from two completely different ISP, which is the internet service providers. If we just use the static routes, we are in the risk of asymmetric routing, where the traffic will leave via one internet service provider but returns via the other. So this will potentially break our firewalls. So with BGP, it allows us to receive the routing tables for both internet service providers and intelligently compare the paths and control exactly how the traffic enters and exits. So last one is handling massive routing tables. The standard protocols are designed to handle maybe a few thousand of routes before they consume too much memory and crash the router. So the global internet routing tables currently host nearly 1 million of the IPv4 routes. So BGP is a protocol that specifically engineered to process the massive routing tables without destroying our hardware. So next, we move on to where does the BGP run?
Okay. So first, logically, BGP runs on boundary routers, specifically the ASBR, Autonomous System Boundary Router, as we can see in our lecture diagram here. the ASBR is the bridge connecting different autonomous systems. And second, physically, oh, sorry, uh, uh, logically here, BGP is an exterior gateway protocol. It operates between different autonomous system AS and not inside a single AS like IGP, like OSPF handle that. And in real world, you will find BGP running on ISP core networks, internet exchange points, and large enterprise edge routers. So BGP, in summary, BGP lives at the edge between ASs, specifically on the ASBRs. That's all.
Okay, so we go to the who will use the BGP. Okay, so BGP is mainly used by organization that manage the large network and large data and need to exchange the routing information with another network outside like outside the country. So for example, internet service provider, which is ISP, use the BGP to connect with other ISP and exchange internet routes to ensure that users can access the website and online service worldwide. So next, cloud service providers, so companies that offer the cloud service use BGP to connect the multiple data centers around the world and provide the relevant global connectivity. Also, for the large enterprise and CDN, content delivery network, use BGP to route user to nearest or efficient server for fastest content delivery. And for last, university and government organization, which is the large institution, use the independent networks and multiple internet connection and use the BGP to manage the external routing to be efficiently.
Now on the BGP works. We look at it as a path vector protocol. Unlike in internal protocol that counts individual router hops, BGP manage routing on a massive scale by treating an entire autonomous system or AS as a single hop. BGP does not discover its neighbor automatically. Instead, peer must be manually configured to establish a highly reliable point-to-point connections over a TCP port 179. Once this connections is active, router communication using four primary message types opened and keep alive to build and maintain the session. Update to dynamically advertise or withdraw network prefix and notifications to instantly terminate a session if an error is detected. Finally, BGP is completely policy driven. It filters these paths using unique path attributes rather than simply choosing the shorter physical link.
Okay, now we move on to the big one of the BGP attributes. So what I found is a local preference. So on the research that I do, what I found about local reference is it is a well-known discretionary parts attributes that is strictly local to an autonomous system, while it is synchronized across all internal IBGP neighbor to influence internal routing. It is completely stripped from the BGP update properties the moment a route is advertised externally to an eBGP peer. In terms of function, its role is to serve as a primary matrix in the BGP best path selection hierarchy. BGP operates on a higher value is preferred rules, using a default baseline value of 100. by applying a routes policy at our transit gateway to inject a higher value such as 200. We force all internal router to mathematically select that specific exit paths over any available alternative. So looking at our topology on the diagram on the right, we have configured AS1 with router 1 hosting the target network 1.1.1.0-24 and AS2 with router R2, R3 and R4. This setup simulates an enterprise core where a client router needs to pick an outbound exit paths toward the provider. Next. Okay, moving on to our live system verification. This highlight how our parts engineering choice reflect directly on the command line interface of R4. First, we verify the BGP control plane parts selection logic by analyzing the output of display BGP routing table. If you can see over there, it has a log preference 200. This confirms that R4 is success learn the modified attribute value via our internal IBGP session. The more than symbol in the first one, it is proof that BGP parts engine selected the R3 parts as the absolute best parts because higher local preference wins. Second, we verify the actual data plane traffic paths to ensure live packets follow the control plane decision by running a trace RT negative A 0.4.4.4.4 and 1.1.1.1. If you can see over there, 192.168.34.3. This is function as our proof of concept. It proved the very first hope exists toward R3. Demonstrate that traffic physically takes our preferred bottom links. Next. Okay, to understand the configuration back-end driving this mechanism, we look directly at the setting on our edge gateway, which is R3. The first command that we do is to display routes policy set local preference. It is to audit our custom policy structure to show exactly how the matrix manipulation rule are built. So as you can see, permit 10 is this allow the matching traffic profile to pass through the filter not successfully. Apply local preference to 100. It is a specific instruction that actively override the standard matrix of 100 up to 200. And the last one is a match count 2. This acts as a live verification counter, showing that the policy is actively working and has successfully caught 2 routing updates from the provider. Move on to the next image. The second command that we do is to display current configuration. No. Back, over there. The second command is we want to display current configuration BGP. It is how want to show where the policy engine is tied directly to the protocol to trigger the metric manipulations. So one of the main things that we look is peer 4.4.4.4 next hop local. This show that R3 changed the BGP next hop attribute to itself before passing external routes to internal IBGP neighbor like R4. Without this, internal router would know how to reach the next hop. And the next thing we look is routes policy set local preference import. This is the execution trigger. It's trigger our policy inbound the exact millisecond external router enter from R1, injecting the value 200 into our control plane before advertising it inside our AS. Next. Okay, next, I think that's all from the local preference that I found on the research. So to summarize this, Local preference is a powerful BGP attribute that aids in granularly modifying routing so that the preferred path is chosen. Because it is the first attribute to be examined, it makes BGP routing more efficient and can supersede any other attribute that may result in unpreferred routing. It is a primary used to modify outgoing traffic. It can also be used to influence incoming traffic with the appropriate agreements between the entities administering neighboring access. I think that's all for the local preference. Thank you.
Okay, the attribute I choose is AS pass. So what is it? The AS pass is a well-known mandatory attribute. It means every BGP routers must support it, and it must be included in every update message. It lists all the AS numbers a route has passed through. And there are two functions. The first is loop prevention. If a router sees its own AS number in the path, it will drop the route immediately. And the second function is path selection. BGP prefers the shortest AS path length. So my goal here was to manipulate the attribute. I want to override the path to make it look longer to the remote router, proving that we can control the BGP's decision-making process. So next slide, please. Okay, now my topology is here. I use 3 Huawei routers, and R1 here on the left side has loopback interface simulating the internal network. So to modify the AS path, I use the route policy on R1 following the Huawei configuration guide. Here is the critical command listed in the annotation here and also on the right side. Apply AS path 100, 100, 100 override. So, and another important thing is the override keyword. This tells the router to replace the original AS path entirely, inserting 3 instances of AS 100. I then applied the policy to outbound direction toward R2 using the peer export command. The configuration is directly mapped from the Huawei documentation ensure that it's syntactically correct for the UNSP environment. So next, please. And the upper graph is the graph which before configuration. The path to 192.168.1.1 was 100, 200, but after applying the route policy, the path changed to the 200, 100, 100,
Wait lah,
100. So by adding these 3 extra 100s, I made the path look artificially longer. So this confirms that my AS path attribute manipulations was successfully implemented and done it. And next. Okay, so to summarize, using the override command, I proved that we can control BGP route selection, and the reference have been listed here. So that's all for AS path.
Okay, so we go to the next attribute, which is the BGP next hope. So what is the BGP next hope? So next hope is a BGP attribute that defines the next router IP address used to reach a destination network. So what is the purpose of this? So this is to identify the next router for forward the packet, help routers to determine the path of the destination network and can be modified to optimize the routing and traffic flow. So they have the eBGP and also iBGP. So it works when the BGP router advertise the route and it include the next hop IP address. So the receiving router checks whether the next hop is reachable. If the next hop is reachable, the route can be installed in routing table. If the next hop is unreachable, the route is not used. Okay, next. Okay, so this is our topology of the next hop, which is we have the three routers and they have in different autonomous system. As you can see in yellow color, we have AS65001 and the pink color AS65002. So they have the different autonomous system and for router one is act role as the eBGP router and router 2 role as the transit router between the eBGP and also iBGP. So for the router 3, it act as the iBGP router. So what is the objective of this topology? So we can demonstrate the next hop attribute in eBGP and iBGP environment and how the next hop local command change the next hop from 10.0.12.1 to 10.0.23.1 which allow R3 to use the route successfully. So okay, next. So after we set up the network configuration, we display the BGP peer to make sure we can know the neighbor of their router. So when, as you can see, when the state is established, it means that the BGP connection are working correctly. So as you can see for the router one, after we click, we enter the display BGP peer, we have the 10.0.12.2, which is the router 2. And same also for router 2, we have the peer of the router 1 and router 3. For router 3, also have the peer for the router 2. Okay, next. Okay, so for the before we configure the next hop local configuration, when we display BGP routing table, uh, R3 received the route of 111 from R2 through an iBGP session. So it is because they have the same autonomous system. So they have in iBGP, internal BGP. So the next hop still remains 10.0.12.1, which is R1 interface address. So this is occurs because iBGP preserve the original next hop by default. So this is iBGP. So since R3 cannot directly reach the 10.12.1, the route is not selected as the best path. As you can see on the red colors, uh, yeah, on the II. So this is not the selected as the best path. So this demonstrate that XHOP reachable problem before applying the solution. So to make sure this problem is okay, we can apply the next hope local configuration. So it is easy, just enter the what as of your BGP, enter the peer 10 or 23.2, which is the router one. So we can have the reachable issue and the with this command we configure on our router 2 and this change the network attribute from the original address uh, into to eBGP. So it can become the transit router. So it on the interface address before advertise the router R3 via iBGP. Okay, next. Okay, so for the validation, we try to display the current configuration on the router 2. So as we can see, it see the peer 10 or 23.2, which is next hope local. So this is in functional. So we change the next hope to router 2 local interface. So we replace the 10 or 12 one with the 10 or 23 one. It is the to ensure that the next hop is directly reachable to the router tree. So it allows the router tree to install the route as the best of. So after the configuration, we enter back the display BGP routing table. As we can see, the problem is successful being dismissed because we can analyze from the next hop. We have changed to the 10 or 12 one to the best solution. So it's on the interface as the next hope. So our tree can directly reach the best path, which is we can have uh, symbol, the symbol, and this confirm that next hope local command successfully resolved for the next hope reachable issue. So for the conclusion, as we can see, in this next home attribute, we can learn that eBGP changed the next hope automatic, but iBGP keeps the original next hope. So eBGP changed the next hope automatic. So by using the next hope local command, we can change the next hope iBGP to become a reachable address to solve the routing problem. Okay, so it's same also with the real world importance, which is when BGP network is in real internet routing in the large enterprise network, if the incorrect setting on the network configuration can cause the traffic black hole, routing loops, or unreachable network. So this technique is to make sure this network local is to make sure the networks is stable and reliable into the domain routing. Okay, that's all from me.
Now, now we'll go to the origin. And what is for the origin attributes? Origin is a well-known mandatory BGP attribute. It tracks how a network route was initially introduced into the BGP route process. The three type of origin is IGP, represented by I. Uh, this is the highest priority path. It occurs when a network is explicitly declared inside of the BGP process using the network command. Next is the EGP, represented by E, an older legacy exterior protocol type that is no longer used in the modern networking. And incomplete, represented by question mark. This has the lowest priority. It marks a route that were redistributed or imported into BGP from external source, such as a direct interface or static routes. The goal of our experience is if a router receives two paths to the same destination, one marked as I and one marked as question mark, it will always prioritize I and not a question mark. So we will use a custom policy to manipulating this flag to control traffic routing. Next. Okay, for the topology, you can see at the top right, we are using two router, which is the AR2220 as the router. So we have on the left we have AR1, and then on the right we have AR2, and then we have two link, which is 10.1.1.0 and 20.1.1.0 as the second link. So I use two to make sure one of them is become I and one of them become the question marks. So after applying the set origin route, the policy impounds the peer 10.1.1.2 or the origin attribute of the 19 192.168.1.1 changed from question mark into an I. So while the remaining routes retain their original question mark origins, conforming the policy targeted on a specific prefix. The command I use is the display BGP routing table on R1 AR1. For the route these, there are three network which is 10.11, 20.1.1, and the 192.168.1.1. But three of them are in question marks, and then after I apply the set origin configurations, you can see that on the lower sides at the 192.168.1.1 it shows an I at there. So it means that the 192 will become the prioritized routing path for them to go into the access to the AR2. So next. So in conclusions, BGP origin attributes before applying the route policy, all target routes origin organizing from AS200 has an origin flag of question mark which is incomplete, indicating they were redistributed natively into BGP. And then after we applying the policy, which is the set origin, the inbound of the route policy, the origin of the 192.168.1.1 was successfully changed into IGP, which is the highest prioritized path. The path selection control, this result shows that the origins already can know which one is the path that it needs to use, which is the I, which is the 192.168.1.1 as the prioritized path. I think that's all for me.
All right, thank you, Stufika. So next we move on to the last attribute of our group, which is atomic aggregate. Just now we have known the four types of BGP attributes, which is docket preference, AS path, next hop, and origin. So for the atomic aggregate, it is like a warning label. So with the four types of attribute just now, they can handle the massive of scale and also the network. But this will create a challenge that in BGP, every time a route will pass through an autonomous system, it will stamp its AS number into the route. So this will comes with a detailed history of exactly where the route has been and is when the router is running. So with the atomic aggregate, we can solve this problem because if we lose the path history, we will risk and creating the routing loops. So we use this atomic aggregate to solve the problems, and we move on to the topology here. I use the 4 router here, which is the router 1 as the middle will connect all the 3 routers, and for the S2 and S3, I've assigned a loopback on it. So S4 it acts as a receiver message. So next we move to the configuration. So how we actually configure in a live environment. So for outer one, which is the most important, it will act as an aggregator, and also I use a command this is a unique command, aggregate 172.168.0.0, and the subnet details suppress. This command what is the function? It is a function that uh, the router one will establish the BGP peering with everyone. So it will receive the specific subnet 32 routes from the AS2 and AS3, and also it will pass those specific routes along to the router 4, but it will summarize it. It will summarize it into the subnet 16, so which is more easier and also shorter. So easy for us to see and also save the resource. Sorry. So for the router 2, actually it's same with router 3, and later I will show. Router 2, it will configure the specific loopback interface on the device to simulate the internal networks. So router 2 will get the specific IP, which is 172.168.10.10 subnet 32 into the BGP. And next, router 3, it will get the specific IP 172.168.20.20 subnet 32 into BGP also. So basically, router 2 and 3, it is the same. The configuration is same. So for router 4, it will act as a receiver, like I said just now. So as you can see here, I display the BGP routing. So you will see the network of the router 4 and also the next hop, which it will receive all the updates from router 1. And router 1 receive all the info from router 2 and 3. So next, this is a result which I try to run on router 4 to try to see what he actually received from the router 1. Alright, so first we will see the atomic aggregate flag. So basically this is a warning label that it will tell router 4 to uh let it know that this is a summarized route that received from router 1. The detail of the ASPARC history of the networks, it is inside the summary and has been intentionally dropped. So next to it, we will see the aggregator ID. So which this is from the AS1 and the router 1 specific IP address. So this is just a ID to let us know. So this will tell router 4 who is dropping the history. So with this, we can receive all the updates from R1 that get from R3 and R3. And in the advantages, we can save memories because all the routes are stored in a one single subnet 16 summary route, which come from subnet 32. And also the network awareness, which is fully aware that aggregation will happen and exactly which router perform it. So in summary, the BGP is the only protocol capable of handling internet scale routing and complex administrative policies. By utilizing the atomic aggregate attribute, we are granted the power of aggressively summarized routes and will keep the routing table keeping small and without sacrificing the safety of the network. So it will strike the perfect balance between the extreme efficiency and strict loop prevention. This will ensure that even when a path history is erased or removed, the network will remain fully aware for that aggregation has occurred. So that's all from us for the BGP. Thank you.